Section 2.3, the non-homogeneous equation. Well, again, let us go back to section 2.1. Note that in section 2.1, we are talking about homogeneous equations only. But what if on the right-hand side, we have some non-zero function? Well, here is section 2.3. Note that on the right-hand side, we have g of t. In this section, we do not discuss how to find the general solution of this equation. We will discuss the structure of the general solution of this equation. Please take a look at the following theorem. This theorem says that the general solution of this non-homogeneous equation is the sum of two pieces. Piece number one is the general solution, but not of this equation. This is the general solution of the corresponding homogeneous equation. The second part is a particular solution of the original non-homogeneous equation. Repeat once again. The general solution of this non-homogeneous equation is equal to the general solution of the corresponding homogeneous equation plus a particular solution of the original non-homogeneous equation. Now, if P of t and Q of t are constants, we know how to find the general solution of the corresponding homogeneous. This is the previous section, this section that we just discussed. The question is how to find a particular solution of the given non-homogeneous equation. This will be discussed next week. As I said, in this section, we discuss only the general structure of y of t. Folks, any questions here?
Why are we adding the general solution to our particular solution? I don't understand why that is.
Well, we don't prove this theorem, but I can give you some idea. Look, if you replace here y by the whole thing, since L is a linear operator, L of the whole thing is L of this plus L of this. But L of this is 0 because this is the general solution of homogeneous. L of psi is G because psi is a particular solution of non-homogeneous. And 0 plus G is G. What do you think?
Yeah, I appreciate that. Yeah, that helps a lot.
All right. So, as I said, we do not prove this theorem here, but the proof of this theorem relies on this lemma. Please take a look at this lemma. If we consider any two particular solutions of our non-homogeneous equation and find their difference, this difference is a solution of the corresponding homogeneous. Here's how we prove it. Well, let y1 and y2 be two particular solutions of non-homogeneous. Now let us find their difference and plug in into the left-hand side of homogeneous. When we plug in their difference into the left-hand side becomes L of y1 minus y2. But remember, L is a linear operator. Therefore, L of the difference is the difference of L's. But now, Y1 is a particular solution of non-homogeneous equation. What does it mean, particular solution? Particular solution means you replace y here, here, and here by y1. You take derivatives, you simplify, 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 you get g of t. It's exactly how we jump from here to here. Since y1 is a particular solution of non-homogeneous, L of y1 is g of t. For the same reason, L of y2, since y2 also a solution of the same non-homogeneous, L of y2 is g of t again. And g minus g is 0. Since L of y1 minus y2 is equal to 0, y1 minus y2 is a solution of the corresponding homogeneous equation. Now let us discuss the following example. Please take a look at this. A non-homogeneous equation here is not given. What is given is 3 particular solutions of this non-homogeneous equation. So equation is not given, only 3 particular solutions are given. Question: find the general solution of this equation. What do we do? First, let us go back to this formula. The general solution is the sum of 2 pieces. The second piece is a particular solution of our non-homogeneous equation. So, this portion is easy. We can replace psi either by psi1 or by psi2 or by psi3. Question is, how to find this portion, the general solution of the corresponding homogeneous equation? Well, in order to find this, we should find y1 and y2. What is y1? What is y2? y1 and y2 are particular, linearly independent solutions of the corresponding homogeneous. Question: how do we find particular, linearly independent solutions of homogeneous? Well, now we use this lemma. This lemma says that the difference of any 2 particular solutions of non-homogeneous is a solution of the corresponding homogeneous. So let us find the difference of, say, psi1 and psi2. It's over here. This minus this is e to t, and by this lemma, e to t is a particular solution of the corresponding homogeneous. Similarly, psi3 minus psi2, which is 1, this minus this is 1, is a particular solution of the corresponding homogeneous equation again. We are not done yet. Note that these 2 particular solutions are linearly independent. We showed it over here. Remember, here in section 2.1, we showed that 1 and e to t are linearly independent. Since these 2 functions are, number 1, solutions of the corresponding homogeneous, and number 2, linearly independent solutions, this is indeed the general solution. And now, We replace y1 by e to t, done. We replace y2 by 1, done. And after all simplifications, we get this. Psi1 is t. Here is the general solution of the non-homogeneous equation. Before you ask questions, let me make 2 remarks. Question number 1. What if we replace psi1 by psi2 or psi3? We'll get a different expression here. However, despite the fact that the corresponding expressions will be different, they will give fundamentally same result. Indeed, let us first replace psi1 by psi2. It's over here. So here is psi2, it's t plus e to t. We leave this portion without change. We just, to avoid confusions, let us replace c1 and c2 by c1 tilde and c2 tilde. Note that if we combine together this and this, we'll get c1 tilde plus 1 times e to t plus c2 tilde plus t. And now, if we replace this by c1 and this by c2, we get absolutely same expression. Similarly, if we replace psi1 by psi3, we will get this. And now combine together these 2 expressions, done. And these 2 expressions, done. Denote this by c1 and this by c2, we get absolutely same expression again. Remark 2. In the same way, we can show that if we replace this y1 and this y2 by any 2 distinct functions from this set, we get the same result. In other words, one can ask the following question. Here we consider psi2 minus psi1, psi3 minus psi2. Why don't we consider psi3 minus psi1? Well, we can. Instead of this and this, as y1 and y2, we can choose any pair out of these 3 functions and then plug in here and here. After all simplifications, we'll come up with fundamentally same result in the same fashion as we do here. Folks, now questions.
Tilde is just another way of selecting an arbitrary constant, right?
Yes, absolutely. Since C1 and C2 are arbitrary constants, this expression, which can be rewritten as this, it looks different, but its nature is fundamentally same as the nature of this expression, because C1 is C1 tilde plus 1 and C2 is C2 tilde. That's it. So it does not matter. We use here psi1 or psi2 or psi3. We'll get fundamentally same result. Same for y1 and y2. We don't have to use just these 2 differences. We can use this and this. We can use this and this. We can use this and this. The reason why we use these 2 differences is the following. The resulting expressions are as simple as possible. Therefore, it's very easy to prove that they are linearly independent. Any other questions?
Yeah, I've got a question about how we're saying that psi of t is the solution to the non-homogeneous equation, when I thought the solution was the like the entire C1 Y1T, C2 Y2T plus psi of t?
Well, it's written 3 solutions. Here are 3 solutions. Psi1 is a solution, psi2 is a solution, psi3 is a solution.
So if we go back to when we were trying to find, or I guess just above there, yeah, just where it's y of t, c1, y1, c, yes. In this case, we're saying that y of t equals psi of 1 or psi of 2.
No. Give me a second. Know that this is a copy of this. In this formula, y of t is the general solution. Here, y of t is the general solution. In this formula, psi of t is a particular solution. Here, psi1 is indeed a particular solution. It's written. In this formula, this is the general solution of the corresponding homogeneous. And here, this is the general solution of the corresponding homogeneous, because this is particular solution and this is particular solution by the lemma. What do you think?
So is the psi of t in the example we're doing not related to the psi of t in the equation at the top of the page?
It is related. Here, psi of t is a particular solution of non-homogeneous equation. Here, same thing. Psi1 of t is a particular solution of non-homogeneous equation.
I guess I thought that the particular solution has to also include the first term, like the c's and the y's.
No. Psi is a particular sum, any solution. Just any solution, but of non-homogeneous. Don't confuse with this. This is the general solution, but not of this, of this.
Okay.
This is the general solution of this. This is a particular solution of this.
Okay.
The nature of these two parts is very different. This is the general solution, but not of the original equation. No. This is the general solution of the corresponding homogeneous. You see it?
Yes. Yeah.
Once again, this is the general solution and this is the general solution. However, this is the general solution of non-homogeneous. This is the general solution of homogeneous. Now, this is no longer the general solution. It's a particular solution of the given non-homogeneous.
Would you say that the y of t that includes the psi term, is that whole phrase, is that a particular solution to the non-homogeneous equation?
Well, since y of t is the general solution, it is a particular solution.
But also psi of t is another different, just alone is a different particular solution to the non-homogeneous equation.
Well, if C1 is 0 and C2 is 0,
okay,
y is equal to psi.
Okay, that makes sense. That helped a lot.
C1 does not have to be 0. C2 does not have to be 0. C1 is some constant. C2 is some constant. You see? This is the difference between y and psi. Psi is some solution. Y is the general solution.
Okay, thank you.
Sure. Other questions?
Okay, you're saying that your general solution for the non-homogeneous equation, you would get the same answer regardless of which psi you use. You could use any of the three.
Absolutely. And I show it here. Please take a look. Instead of psi1, let me use psi2. Psi2 is equal to this. So we replace psi2 by this. Okay? Now, obviously, this expression is different from this. It looks different. However, if we combine this and this, we'll get this. And now if we replace this by C1 and this by C2, we get absolutely same expression.
Right. Okay. That makes sense. Thank you.
Other questions?
Can you scroll up a bit?
Yes.
Okay, so where it says proof, let y1, y2 be two solutions and by the linearity. I don't exactly understand why L of y1 and L of y2 are both exactly equal to g of t.
Excellent question.
And what is g of t? Like,
Yes. Another excellent question. Please take a look at this. Y1 and Y2 are two solutions of 1. What is 1? It's this equation, correct?
Yeah.
Now let us think about what does it mean Y1 is a solution. A solution means you replace Y here, here, and here by Y1. You take the derivatives, you simplify on the left, and you get the right-hand side, correct?
Oh, yeah. I see.
So L of Y1 is this when we replace Y by Y1. After all simplifications, it is equal to G of T, the right-hand side, correct?
Yeah.
Since Y2 is a solution, L of Y2 is also G of T. Done?
Yeah, I just noticed above that. That's why it says g of t there. Okay.